So this is joint work with Yuri de Ruiter, it's a PhD student of mine. He recently moved to the University of Birmingham, and Alexis Schubert, who's at the University of Warsaw. But it's actually building on a lot of work I've been doing over the past 10, 15 years, where we've been trying to do, on the one hand, formal analysis. So my background is in formal methods, so we've tried formal verification of software, formal analysis of protocol, but also a lot of ad hoc security analysis, where typically formal methods is not the quickest way you find the bugs, so more ad hoc things. And one thing I found there is that sort of my favorite formalism here is not EBNF grammars, it's state machines. So I found that state machines were a really useful tool in understanding these systems. So this is why I sort of look at LangSec from this perspective. So the motivation for this, as Sergey already indicated, so if you're handling inputs, you're typically getting these input messages according to some formats. So these are, of course, SSH packets, which are sort of crawling with length fields, which some people don't approve of here, I understand. But just so you can, so this is one part of the problem. But the second step is that, okay, after you get these messages, you also have to set up a session, and then typically people come up with these sorts of pictures to show that there is some notion of session and a particular sequence of messages that you're expecting and that you have to interpret. And so basically what we try to do in our paper is trying to see, so do the same LangSec principles also apply at this level of session languages? So when you look at the problems of specifying this or verifying this, and of course our answer will be yes, or at least that's what we will try to hope to convince you of. So just an indication of sort of the formalisms people use for session languages. So typically we notice them in specifications as message sequence charts, so which describe sort of a happy flow of a complete session. And this is a useful specification, but of course you should realize that it's typically a very incomplete specification, because you're only giving one example of one correct happy flow, and you're not saying, okay, what if something else happens? Another formalism which I prefer, which I think is slightly better, is just a state machine. So this was SSH. This is a model of SSH as a state machine. So we made this sort of after reading the RFCs for a while. So here we noticed that there's actually different correct flows. And there's actually a cycle there, because in SSH you can do key renegotiation where you sort of jump back. So this is a useful formalism, I think. But even though here, for instance, there are several happy flows, it is still oversimplistic, because you're still ignoring, you're not saying anything about what happens in the other cases. Because of course, in general, if you implement the protocol, you will have to handle arbitrary sequences of messages, also incorrect ones. So typically you will have to give a state machine, which in the technical term is input enabled, which is basically saying that in every state, you have to be able to accept any message. And of course, the bulk of these messages are incorrect, and you will have to abort or reset the protocol. And only the happy ones will sort of get you towards nirvana at the end, where you can actually exchange data. So, so just a visual indication. So this is a pattern you typically see in these input-enabled state machines, that you have sort of a normal flow, and then here you have all these red arrows, which are, for instance, error transitions. And a typical response is that if you get an error, you jump back to the beginning of the session. Another pattern you see is that you jump to some error state and you never return from it. Or you will see examples later of where you basically ignore the funny messages. So these are sort of patterns you see coming up. So we've been looking at different sort of products and protocols and pieces of software and hardware, and then we've trying to use state machines to describe their behavior, to do some formal analysis. And over the years, we found some interesting security flaws, which are basically due to a broken state machine. So the funniest example was a MIDP SSH. I don't know if anybody here still remembers Java feature phones. We did software verification of Java feature phones 10 years ago. There was somebody who implemented SSH on a Java feature phone, so we thought we'd verify this. And the ironic thing is, so we spent a few days poring over the RFCs to come up with a state machine, and then we wanted to formally verify using a program verification tool that this implementation actually correctly implemented the finite state machine. And then to our surprise, we found out that the implementers forgot about the state machine. So they wrote a lot of input handling functions to correctly take the packets from SSH, check all the MACs, but completely forget about getting the packets in the right order, which is a bit of a security worry if you're doing SSH, because all the protocol layers of SSH is one big protocol, so you could ask the user to authenticate before there was a session key. And yeah, so it was a bit of a shame that all our efforts in trying to formalize SSH were sort of useless, at least for the point of verifying this. But this was sort of a small open source software project of somebody who just got a Java feature phone. A slightly more interesting one, and I think a more embarrassing one for the producers, was a USB connected internet banking device. So this is a device that you get from one of the Dutch banks, which you hook up with the USB interface to your laptop. You stick in your bank card, you type in your PIN code, and then when you transfer money, the details of the bank transfer are not shown on your laptop screen, but are shown on this separate display. And you actually have to press OK on this special device to confirm the transfer. So this can defeat many of the browser attacks. Of course, this thing is connected by USB, so an attacker might be able to hack it, but it's going to be very hard because there's not Windows running on there or a Firefox browser. And to our surprise, we weren't trying to hack the device. We wanted to use it and to reverse engineer to use it. And then we found out it was broken because, so the security critical functionality here is that you have to press OK on this device. And then we found that by sending some strange sequence of USB commands, you could actually press OK from the laptop, which is sort of defeating the whole purpose of the device. Yeah, so we started looking at banking products maybe 10 years ago, I think. When I started, it was my naive expectation that, of course, these people have looked at security, but I mean, I guess somebody did a security review, but they were probably asleep for most of the time. And then earlier this week, there was a presentation by the researchers from INRIA on research on TLS that they've done. And they found sort of a lot of messy state machines in TLS implementations. And for instance, they found the freak attacks. I'll show some examples of TLS later, because we also did a bunch of experiments with TLS and found lots of more bugs there. So one of the frustrations is if you try to get a good understanding of the session language and you start looking at specifications, then you typically find that it's written in prose. So these are some quotes from the SSH specifications. So where they give some they give some prose to basically give constraints on the order of messages that can or cannot occur. So this is sort of this is giving a constraint for doing the key exchange, that after sending a certain message, then until you receive another message or send another message, you should only be getting key exchange messages. Now the annoying thing with these specifications is that, of course, if you take the RFCs from SSH together, I think it's about 200-300 pages. There are statements like this throughout the 300 pages, right? So you have to read all of it and try to cobble it together to understand what is really the state machine that you have to implement. For instance, one of the funny things in SSH, we noticed that there is this notion of an unrecognized message. So if you get a message which you don't recognize, you have to say back to the other party that you don't implement this. But it's actually very hard to find out what the unrecognized messages should be, right? If you get a message from a higher protocol layer in the wrong order, is this then unrecognized, or should you ignore it, or should you respond to it with saying you don't implement it? So the bottom line is that understanding the state machines from this kind of prose can be very hard. And then SSH is not the most complex protocol out there. So at some stage when we were looking at SSH, we also thought, okay, let's look at some source code to see if we understand it correctly. And for SSH, sort of open SSH is sort of a default implementation. So we looked at OpenSSH. It's not that big. It's about over a few hundred source files. Now, of course, there is some state machine implemented in this code, and we started looking for the state machine. Now, there's many ways you can implement a state machine, right? You could have like 20 Boolean flags, or you could have one state variable. So the nice thing is in OpenSSH there's only one state variable and there's only about a dozen or so files which actually touch this state variable. The not so nice thing about this state variable is that it's an array of function pointers with 255 function pointers to be exact. And so the way OpenSSH works is you get an SSH packet, you look at one byte in the packet which is giving the message type, and then you use this table to jump to some routine that handles that packet. And then, so this gets initialized at some stage, and then during the protocol run, you update this table in various entries. Now this is sort of very efficient and very clever, but actually understanding the state machine from the code is very horrendous. I mean the state space, you know, you're talking maybe about a few dozen states. I mean, of course, if you have this array of 255 elements, you know, the potential state space is something like 2 to the power 32 or 64 to the power 255. And actually tracing this through the source code is really, really painful to try and understand this. So we did a manual code review of OpenSSH. We did not find any bugs, at least for the transport layer, but I wouldn't make any serious bets on this. And I think you want to implement this in a cleverer way. So this can be very hard. And I guess sort of the first thing that I would like to propose here is that saying that, okay, these protocol state machines, they're important and they deserve to be explicitly specified. So it's my guess is that people who design protocols, typically they have a whiteboard which looks like this. So they've written up their finite state machine. But then when they type in the RFC, of course, it's really hard to type this in an RFC. So you leave it out. And then you get a bunch of pros. And then the people who have to implement the protocol, they read all the pros. They go to their whiteboard again and then they start redrawing the diagram. If you're lucky, it's identical diagram, but of course the chances are that it's slightly different. And I mean, you can avoid this by just sticking the state machine in the spec. So now John Postel has been getting some stick for the Postel principle, but actually if you look at the TCP specification, it actually includes a state diagram, which is then drawn in ASCII art, because of course an RFC has to be ASCII, but you can actually draw the state machine in ASCII art, and they actually did that. And that's really useful to have. So looking at some protocols, so we looked at some known protocols, but we also looked at some unknown protocols to reverse engineer them. And now we find out that there's actually a really nice trick to get a state machine from code. So this morning there was a talk, you mentioned an algorithm by Al Gruin to do inference. So there's a really nice algorithm called L star, which is about, by black box testing a system, you try to extract a state machine that's implemented in the system. So this is the L star algorithm dates back to the 1980s, and there's a couple of libraries that actually implement this off the shelf. So we typically use LearnLib, which is by the people from Bernard Steffen's group in the University of Dortmund. And basically what this learning technique is doing, it's basically sort of a fuzzing technique. You're trying to fuzz the system, and based on the responses, you're trying to learn the behavior of the system. And so you have to provide an interface which actually will send the messages, or test harness, which will send some typical protocol messages and get a response. But then you can use this test harness and LearnLib, and just by black box testing, you come back after half an hour or a day, and you have a state machine out there. So this is really nice to get there, and it's nice maybe to implement, to show the idea of the protocol. It's nice to actually do some formal language theory in the talk, because the basic principle is very simple. Suppose I have a system which has two input actions, A and B. Now what I can do, for instance, I can test, as a test I can give it the input A, or I could give it the input B, or I could give it the input B preceded by an A. And the idea of the algorithm is you try both options, and then you look if you get a different response. Now, if I get a different response in the second case to the B, this means that the first A that I sent caused an internal state change. So if I get a different answer after the B, then I know the state machine looks something like this, because there is a transition for the A. If I don't get a different response, then my conjecture could be that this is the state machine, sort of doing an A is not going to make a difference. So this is the whole idea of the algorithm, and then you just keep repeating this. Now the algorithm is not perfect in a sense that it's very difficult to exclude the fact that if I try 10,000 A's, maybe then I will cause a state change. So there is some limitations on how accurately you will model the system. So you only get an abstraction of the system. And of course, if there's an input action C and I'm not trying it out, I don't learn anything about the state space that has to do with this. So the state machine that you can get out is only as good as your approximation. It's only an approximation, and it's only as good as the test interface that you have. How many messages are you trying to give? So the first example where we tried this, which was really successful, was EMV. EMV stands for Europay MasterCard Visa. And if you have a bank card in your pocket which has a chip in there, you can bet that it's implementing a variant of EMV. Yesterday there was in the news here that skimming in the US is going up, like copying magnetic stripes, which is not a surprise because of course all the criminals have moved to Europe now and they come to do it here. So they will be rolling out EMV chip cards in the States also. The EMV spec is a bit nastier than SSH. The specification is in 4 books, which is totaling over 700 pages. And it's not really a standard because I think it's sort of more of a protocol tool suite kit because it's defining lots of bits and pieces that you could use to cobble together to implement a banking card. So there's now also a contactless version of this, which is worse because then they have actually seven books with 7 different standards, which are partly compatible. So the specs are public, but only in the sense that they define the message format, they don't define the state machines. So we wanted to understand it a bit better. So we wrote a test harness which basically tries out some standard EMV commands and looks at the response. And this is only 300 lines of code. And then if we use this test harness and learn it and we test it using this algorithm for like 20 minutes, then we get out a state diagram of your bank card. So this is a state machine of a German Volksbank card. So my university is very close to the German border, so we have people with banks across the border and we can try different cards. So this is what you get out in half an hour or so. You can clearly identify that there's a handful of states, 8 or so. The little clouds of arrows that you see in a lot of states, this is what I mentioned, because the thing has to be input enabled. And there are a lot of messages here in the protocol that if you send them at the wrong time, they get ignored. So this actually, if you try to print this off at a readable font size, it becomes very, very wide. So we do some tricks to make it a bit more readable. If you simply merge all the arrows which give the same response, so a lot of these arrows, these little circles, they will give you a standard error response. If you combine these, you get something which is a bit more legible. And actually, if you combine all the arrows with the same input and with the same begin state and end state, you get a very readable format of actually the protocol. And so this is a very nice formalism then to use as a basis for understanding, is this implementation of EMV secure? So to our disappointment, we did not find any security bugs in the code, but we found a bizarre variety of state machines between cards. So it's my experience that if I take my Dutch EMV card and I stick it into an ATM anywhere in the world, I get money out. So presumably there's a lot, all the state machines of all the cards are different. So my guess is that they all use some happy flow, and a lot of the state that's actually there is actually redundant. But we didn't find any security bugs. Now we did find the security bug in this internet banking device I showed earlier. So we also did state machine inference for this device. So the bank actually patched the device. Of course, the thing, they had to actually give new copies to the clients because you can't remotely update it. They had several million of them in the Netherlands. And we inferred a state machine, and here on the left you see the original state machine, and on the right you see the state machine of the patch device. The red arrow there is the security flaw that they had. So they trimmed the state machine in the new implementation to get rid of the security bug. One of the funny things about this work was that to do the fuzzing here, we have to press the buttons. And so I had some students, they actually used Lego to make a little Lego robot with 3 fingers which can press the buttons. So we only need 3 fingers, one for OK, one for cancel, and one for the pin code. And then our pin code is always 1111 because then we only need 1 finger. And so I was worried that learning the state machine of this device would take weeks because it's not a very fast robot that we built. But actually these 2 state machines, they're obtained within 2 to 3 hours. So this actually works. And the only problem that we had is that when we ran more extensive tests, some of the buttons of the machine, of the little device would become, would wear out, right? Especially the one for the pin code. So we had to change the device for a while. Yeah. So we actually have a nice movie on YouTube. I think this is my favorite paper because it combines formal method security and Lego. So where do you get that from? So, of course, so we could confirm that they got rid of this one security vulnerability, but then we wanted to look if there were other security vulnerabilities. So we also ran a more extreme test on the new device where we used a richer input alphabet. And then, to our surprise, we got out this state machine. So the device basically only has to look if you pressed OK or not, because actually the checking of the pin code is done by the smart card. So we have no idea why this device is so complicated. You can just about manually try to verify that it is secure, but what we actually did is we fed this state machine to a model checker and then expressed the security property in temporal logic and automatically verified it. So we couldn't find more security flaws, but this sort of complexity is a bit worrying, I think, because, I mean, yeah, I don't expect that the people who developed this had any clue that this is what they implemented or designed, and that they were really confident that it was secure. And my guess is that there's a lot of branches in this state machine that are completely unnecessary. So earlier last year, there were some issues with TLS. And so we also said, okay, let's have a look at TLS. TLS is, of course, a very important protocol, so you expect people have thought about the state machine for a lot. And so we wrote a test harness to test TLS servers, and then we tried out different ones. So this is the state machine of the NSS implementation. And this is actually quite a nice state machine. So the green transitions here, this is a normal, successful TLS handshake followed by a small session. And all the other arrows are basically erroneous transitions where you sort of get kicked back to some error state at the end. So this was, from a security point of view, this is a nice implementation because the specification is so simple. But then GNU TLS looks like this. So we discovered a funny bug in the GNU TLS was that, so TLS is a nice trick that after you do the handshake, both parties compute a hash over the entire handshake, this all the sequences of handshake messages, and they send this across to each other to verify that the handshake was successful. And then you can also really rule out any man-in-the-middle attacks because you've both seen the same hash. Now we found out that apparently the buffer that's used to compute this hash is also used by the heartbeat functionality. So if you send a heartbeat during the key exchange, which is probably a silly idea, but I'm not sure if it's disallowed by the spec, yeah, you can actually screw up this value. So you could do a man-in-the-middle attack on a GNU TLS server and a client which has the same vulnerability. You could do a man-in-the-middle attack, and then at the end of the key exchange, send both of them a heartbeat message to reset this buffer, and then they send an empty hash or a hash over an empty string to each other, and they agree. But then, of course, it can get worse. So this is the state machine for OpenSSL. So this is, of course, so I'm not sure how many of you saw the talk earlier this week by the people from INRIA. Here in TLS, we're only trying one cipher, one set of key exchange algorithms and one set of crypto algorithms. So you're doing one variant, and we're just doing the full handshake, not the abbreviated ones. So it was actually surprising that if you look to more mature implementations of SSL, we found that the state machines become more complicated. One conjecture could be that the code's been around for longer and people have been messing with the code for a long time, and there's all this spurious complexity in there. And then the worst one we found was Java Secure Socket Exchange, because there we could actually see so this is a state machine that we learn, the red arrows there, this is already a security problem because you end up in the correct state, or a seemingly correct state, but not by completing the full handshake. And this is also where the freak vulnerability comes in. And then we tried 7 or 8 or so TLS implementations, and none of them have the same state machine. And my guess is that the one on the bottom right is the best, and all the other ones, I mean, you could trim the source code to get rid of all the extra junk.
Which one is on the bottom right?
I think this is the NSS one. Yeah. And of course, if there is redundant state, it's not trivial to check if there was a security vulnerability. So we found one thing that could be exploited and 2 things which could probably not be exploited. But these extra states shouldn't be there, right? You shouldn't be worrying about this sort of behavior. Okay, so to come up to my conclusion, so I'd like to argue that, I mean, the same LangSec principles that are useful when looking at processing input messages are also useful when you're looking at the session languages and processing sequences of messages, because, okay, we see the same issues, that the specifications are not clear. You see a lot of variation in implementations and some security bugs because of this. So what's not really clear to me yet is sort of how common this category of security flaws are, but my guess is that there's more out there. So if you then compare the notion of the session language with the notion of the message format or the language, I think, so a lot of specs, they will have an EBNF somewhere in an appendix, but I think the state machines are actually less likely to be rigorously specified. One practical problem I notice is that actually giving a complete state machine, I think, is actually harder in most cases than writing an EBNF grammar, because especially handling all the error transitions, and because you have to come up with an input-enabled state machine, actually doing this in practice is a bit of a challenge. So I'm not sure in practice what is the best way of doing this. And what I also think is more difficult for session languages is generating code. So it's trivial if you have an EBNF grammar to spit out some code. Now, of course, if you have a state machine, you could spit out some code, but this code still has to be merged with some existing code, because there is more to handling the session than just determining what type of input messages you have. So if you have a language where you have, for instance, aspect orientation, you might be able to factor out the state machine as a separate aspect. But in general, I think that to handle the state machine, you will need some sort of a scattershot approach, because there will be different pieces of code handling this at various places. So I think the good news is, what I've shown you is that it's actually quite easy to extract state machines for a lot of existing protocols. So this morning it was mentioned that in practice with grammar learning you can actually learn a lot of input alphabets. I think it's even easier for state machines because in practice they're not quite as wild. Of course, if somebody actually makes a malicious backdoor in the code, you're not going to find it using the state machine inference. But if there's an accidental flaw in the program logic, it will typically show up. That's sort of my gut feeling. And finally, if you look at the danger from the perspective of providing a weird machine to an attacker, I think that if you have a bug in the state machine, typically somebody can bypass some security check, or they can access some functionality they should not be able to access. But I don't think you are likely to provide a lot of, a very rich, computationally rich weird machine to your attacker. So I think sort of the weird state machines that we've seen are not really weird machines in the sense that you can actually easily program them or do a lot of programming with them. Okay, and so to end in good LangSec tradition, I would like to start with
we'll take questions now. Yes, this is excellent.
So actually, I got started on LangSec by actually somebody giving a presentation and using one of these slides from I think the CCC presentation, and this got me hooked on. Oh, let me find out what this is.
Hey, Julien Bloomberg. Great talk, very entertaining. I have a question about the EMV and all of this you've done. So you mentioned that you didn't find any vulnerabilities. However, all the state machines are different.
Yeah.
So do you know if they are equivalent in some way? For example, are they equivalent up to traces or equivalent up to observations or something like that?
No, and I know some machines are really different, but also because the EMV is not a single protocol, but it's sort of a family of protocols. And in some settings, the protocol, so on a typical bank card, there are actually multiple EMV implementations, and they actually enforce different security policies. So the simplest example is that, so there's an application on Dutch EMV cards which we use for internet banking, and in this case the PIN is verified offline, typically because the internet banking device is offline, whereas for an ATM, the PIN verification might be done online, and then it's not checked by the card. So there is some explanation for some of the differences, but not for all of them.
Okay. Also, second question: did you have to look manually at the state machines to figure out whether you had a vulnerability, or did you have some sort of automated?
So in practice, so the only example where we used the model check was the one I showed you at the end, which was getting a bit complicated and boring to do by hand. And
Okay.
typically, we've done it with a manual analysis.
Thank you.
Thanks.
I had the opposite intuition about this method's ability to detect backdoors. I'm just curious, do you think that it would have difficulty detecting backdoors just because they're so well hidden and the automatic discovery of the state machine wouldn't find them, or?
Yeah. So when you're learning the state machine, you're sending typical messages of a certain type, but the backdoor might be triggered with a very specific payload. Like for instance, in the SSH, there will be random numbers that you throw in during the key exchange. We are not going to try all the random numbers, and maybe you open the back door with one of these random numbers. So you're never going to find this just by blindly testing. So one thing you might try to do is, for instance, combine. But then it's no longer a white box approach, but more of a black box approach, but more of a gray box approach. When you're learning the state machine, you could, for instance, look if there's pieces of the code that you don't reach. And that might be a giveaway that either there's dead code in the implementation, which is of course not inconceivable, but that could also then be a backdoor because you're not triggering that functionality.
Just real quick, I've been thinking about how to specify protocol state machines and how to generate code from them. Since you mentioned this only in the end, the question is, how much work have you done on this, and will you continue in this direction?
So we actually, the first work we've done, but that's like 12 years ago, we actually had some tooling to generate state machines from code. So we had a tool where we generated Java smart card code from state machines, and also actually method contracts that we could verify that if you change the code afterwards, they were still correct. There are some other alternatives. There's the system called Rachel, which tries to do generation of state machines. And I guess if you look at any of the UML suite of tools, they can probably generate some code from state machines. But it's not something I plan to be working on, because in the end, it's not very nice. I mean, because you still have to intersperse it with normal code. So for instance, in Rachel, you specify the state machine, and then bits of C code which you stick on the transactions, which is still a bit,
Okay, thank you.
Just a comment. There seems like there's a new area of research, the study of encoding the whiteboard as an RFC and then parsing out back to the whiteboard. And I propose we call this meta LangSec.
yeah. I think one of the big progresses of smartphones is that people can take photographs of whiteboards. And
Different whiteboard in the end, that's the whole problem.
Another thing about the Xerox JB2 scanning, like was floating around today.
We're failing.
I was just saying about scanning whiteboards and cell phones taking images. I just noticed floating on my tweet stream today, there's yet another round of articles and commentary about the JBig2 bug in the Xerox Document Center scanners and the patchwork algorithm that they use for compression. So that's, yeah,